Good day everyone and welcome to our next lesson. In this video, we will be discussing the basic principles of heat engines and heat pumps, as well as their maximum possible efficiency. This is an introductory lesson before we dive into the mechanics of energy generation from heat and refrigeration. Let's begin. Let us first define what is a heat engine. A heat engine is a device that operates in a cycle consisting of four reversible steps wherein the end result is the transfer of heat from a high temperature reservoir to a low temperature reservoir along with the generation of work. It is very important that we associate a heat engine with the generation of work coming from heat energy. The same spontaneous heat transfer from a hot body to a cold body achieved in only one step will not generate work because it is an irreversible process. In contrast, the four reversible steps of a heat engine has the capacity to perform work. Let us take a look at the steps of the cycle in a heat engine to determine how it generates work. First, the working fluid is compressed adiabatically, which is a product of the fourth step, which we will take a look later. Second, the fluid expands isothermally as a result of the absorption of heat. It then expands adiabatically, that's the third step. This adiabatic expansion results to the generation of work. And afterwards, we enter the fourth step, which is an isothermal compression brought about by the release of heat to the low temperature reservoir. As you can see, the heat was transferred from the high temperature body to the low temperature body, although indirectly, but that indirect transfer of energy resulted to the performance of work. The work was generated on one of the intermediate steps, specifically on the third step, that is adiabatic expansion of the gas. We can understand more if we take a look at the framework for heat engines given here. Earlier, we defined a heat engine that takes heat from a high temperature reservoir with the net generation of work and with the rejection of heat to a low temperature reservoir. The four steps taken by the working fluid can be illustrated in either a pressure volume diagram or a temperature entropy diagram. Let's first consider this PV diagram. The two isothermal steps are shown here, that is isothermal expansion and isothermal compression. In the isothermal expansion step, this is where heat is absorbed from the high temperature reservoir to the working fluid, while on the isothermal compression step, heat is rejected from the working fluid to your low temperature reservoir. In this case, work could both be generated and consumed in your adiabatic steps. Remember that we have two adiabatic steps, that is adiabatic expansion and adiabatic compression. Now, since all of these steps are reversible, we can also refer to them as isentropic expansion and isentropic compression. It is in the isentropic expansion step that we generate the useful work. In some variations of the cycle, there is also work input during the isentropic compression, but we will deal with that with our future lessons. For now, the only work involved is the one coming from the isentropic expansion. If you take a look at the temperature entropy diagram, it is easier to characterize your four steps as two being isothermal and two being isentropic. Isothermal means constant temperature. Those are your horizontal lines in the TS diagram. While isentropic means that you have constant entropy, and those are our vertical lines in our temperature entropy diagram. The shape of this thermodynamic cycle is a rectangle in the temperature entropy diagram. A common example of a heat engine is the simple steam power plant, which is illustrated here. Water is our working fluid because water is the one circulating through the entire process. Isothermal expansion happens at the boiler wherein the water is evaporated, transforming it into steam. The isentropic expansion happens at the turbine wherein the expansion of steam drives a shaft, thus generating shaft work. The isothermal compression happens in the condenser wherein steam is condensed into liquid water, thereby compressing it. And the last step, isentropic compression, is happening at the pump here that is used to carry water from the condenser to the boiler. For this process, here we define the thermal efficiency of a heat engine that we will use to characterize power cycles in our next lesson. We say that the thermal efficiency is the ratio of what we get over what we paid for. Considering the steam power plant, we get the net shaft work generated. This is what we want. While in order to obtain that shaft work, we need to pay for the heat transfer from the high temperature reservoir. This is from the combustion of the fuel needed to heat the water in the boiler. That makes our thermal efficiency equal to shaft work over heat transfer from the hot reservoir. If we apply the energy balance, that's energy coming in, that is Q sub H, is equal to the total energy coming out, that is work plus QC, or the heat generated to the cold reservoir, we can substitute this to our thermal efficiency equation, and we have the following. We have QH minus QC all over QH. Factoring out QH, we can simplify this further into 1 minus QC over QH. This is the thermal efficiency of a heat engine. We simply need to know how much heat is being rejected to the cold reservoir and how much heat is being absorbed from the hot reservoir. Do not get confused because sometimes Q sub C can also be represented as Q sub L, representing the heat transfer to the low temperature reservoir. Next, let us describe heat pumps and refrigerators. These devices are the opposite of heat engines, where they have the same four steps but are carried out in reverse. This results to the transfer of heat from a low temperature reservoir to a high temperature reservoir. This is something we know is impossible to be spontaneous because of the second law of thermodynamics. Remember that the second law of thermodynamics states that the spontaneous transfer of energy can only happen from a high temperature body to a low temperature body. However, in this case, this process becomes possible because we are inputting energy, that is a work input. The provision of work allows for the transfer of heat in the reverse of the spontaneous direction. Heat pumps and refrigerators are both examples of this. They have the same working principle, but we differentiate them based on their different outputs. Basically, we only differentiate heat pumps from refrigerators based on what we want from them. For example, for heat pumps, these are your space heaters. We want QH, or the heat transfer to the hot reservoir. Basically, you are keeping a space hotter than the outside. On the other hand, we have the refrigerator wherein we want the QC, or the heat absorbed from the cold reservoir. That's because we want to keep the inside space cold compared to the outside space. Okay, that's the only difference between heat pumps and refrigerators. This image describes the basic working principle of heat pumps and refrigerators. We start with the isentropic compression of your refrigerant fluid in the compressor, then isothermal compression in the condenser, then isentropic expansion in the turbine, and then isothermal expansion in the evaporator. If you notice for this diagram for a heat pump, the evaporator absorbs energy from the cold reservoir, whereas the condenser releases energy to our hot reservoir. If you imagine this as an air conditioning unit, the evaporator is in the front of the air conditioner wherein it gives off cold air, and the condenser is at the back side of the air conditioner because it gives off hot air. If you imagine it like that, it would be easier for you to understand heat pumps and refrigerators. For both heat pumps and refrigerators, we characterize their efficiency with the coefficient of performance. It's either represented as COP, coefficient of performance, or beta. The difference between the COP of the heat pumps and refrigerators, because remember, we want different things from heat pumps and refrigerators. For a heat pump, we want the heat transfer to the hot reservoir, so that is QH over W, because we are paying for the work. In this case, this is electrical work being inputted to the system. For the refrigerators, the coefficient of performance is QC over W, because we want the heat transfer from the cold space, and we are paying for the input work. Therefore, here we have our two equations for the COP of heat pumps and refrigerators. Now, for heat engines, heat pumps, and refrigerators, we can describe an ideal behavior of those processes. The ideal processes of the heat engine and heat pump, previously discussed, are collectively known as the Carnot cycle. And the ideality of the process is apparent with the two isentropic processes in the cycle. Remember, we have isentropic compression and isentropic expansion. The Carnot cycle is a purely theoretical construct, and it cannot be achieved by our machinery because of the inherent consequence of the second law of thermodynamics. The Carnot cycle was conceptualized by Nicolas Leonard Sadi Carnot as the cycle that gives the maximum efficiency for extraction of work from heat, that is for heat engines, or the maximum efficiency of conversion of work to non-spontaneous heat transfer, that is for heat pumps and refrigerators. It is important to take note that the Carnot cycle applies to heat engines, while the reverse Carnot cycle applies to heat pumps and refrigerators. Let us now define the Carnot efficiency. The Carnot efficiency of a heat engine is defined in terms of the temperatures of its reservoirs, that is, the temperature of the hot reservoir, TH, and the temperature of the cold reservoir, TC. If you will remember, the efficiency of a heat engine is equal to 1 minus QC over QH. That is the heat transfer to the cold reservoir over the heat transfer from the hot reservoir. In the case of the Carnot efficiency, we only need to know the temperatures of the reservoir. This becomes 1 minus TC over TH. Now, this is what you need to remember. The Carnot efficiency, or the maximum possible efficiency in this case, is higher for larger temperature differences between reservoirs. For steam power plants, the efficiency of work extraction from heat is increased if the temperature difference between the hot and cold sinks is increased. If we go back to the layout of the steam power plants, your hot reservoir is in the boiler, wherein the combustion of fuel supplies the heat needed to vaporize our water. And the cold reservoir is in the condenser, wherein we are condensing the steam coming out of the turbine in order for us to have a lower value of TC. If we want the power plant to be more efficient, we could either increase further the value of TH or decrease further the value of TC. The effect of changing the temperature difference is shown in this plot. If we look at the behavior of the Carnot efficiency on your y-axis and the temperature difference between the hot and cold reservoirs in the x-axis, the rate of increase in the maximum efficiency is greater at low temperature differences compared to high temperature differences. This means that in some practical cases, the effort and expenses incurred for increasing the temperature difference does not equate to a reciprocal amount of increase in efficiency because of this nonlinear behavior. Most steam power plants have an overall thermal efficiency of less than 35%. Please do take note of that value as the actual efficiency of majority of steam power plants. The Carnot efficiency would of course be higher because the Carnot efficiency is the ideal efficiency of the cycle. If we take a look at the Carnot efficiency for heat pumps and refrigerators, likewise, we can define the coefficient of performance of both using temperatures of the cold and hot reservoirs. So from these equations, the temperature difference is already apparent in the denominator. What happens is if we increase the temperature difference, the coefficient of performance would go down. And for coefficient of performance, we want to have as high value as possible. So the higher the COP, the better the process. So if we want a high value of COP, we want a low value of the temperature difference. In contrast to heat engines, the Carnot efficiency of heat pumps and refrigerators increases as the temperature difference between the reservoirs decreases. This should make sense because the efficiency of your air conditioner will be higher if your temperature setting is close to the outside temperature, in theory. And the same is true for refrigerators. However, if we do that, we are defeating the purpose of air conditioning and refrigeration. Let's say, for example, if the outside temperature is already 20 degrees Celsius, I don't think you will be using your air conditioning system to keep the room temperature at 19 degrees Celsius just to have a high efficiency. Here we have a plot of the Carnot COP versus the temperature difference of the high temperature and low temperature sinks. This tells us that a high maximum COP is obtained when having heat sinks with low temperature differences, and the Carnot COP quickly decreases as your temperature differences increases. A practical understanding of this is that the efficiency to convert work into non-spontaneous heat transfer decreases as the temperature gradient increases. For example, your air conditioning units would need to work harder to maintain room temperature at 25 degrees Celsius if the temperature outside is 40 degrees Celsius compared to when the temperature outside is only 30 degrees Celsius. Okay? So that is the effect of temperature differences on both the Carnot COP and the Carnot efficiency. Let's try to solve some examples. Number 1. Determine the best possible efficiency of an air conditioning unit that keeps a room at 20 degrees Celsius while the outside noontime temperature is 33 degrees Celsius. Here we have our given to the problem. So you are given a refrigerator. It's an air conditioning unit that was designed to keep the temperature of the cold space at 20 degrees Celsius while the outside temperature is 33 degrees Celsius. This is the diagram for a refrigerator wherein we have an input of work in order to drive the heat transfer from the low temperature reservoir to the high temperature reservoir. The problem asks us to determine the Carnot COP or the maximum possible efficiency for this refrigerator. For that, we recall the COP of a refrigerator is equal to what we want over what we paid for. What we want is the cooling or the heat transfer from the cold space over what we paid for, that is the work input. This is for a refrigerator. For a Carnot refrigerator, we simply have to substitute the temperatures instead of the energy flows. Before we do that, let's first express our work input in terms of the heat flows. For our energy balance, we have our energy input, work, plus another input that is QC, and our output is QH. Rearranging this is W is equal to QH minus QC. Therefore, that will be our denominator in our coefficient of performance, QH minus QC. Our expression for the Carnot COP of our refrigerator is now TC, or the temperature of the cold reservoir, divided by the temperature of the hot reservoir minus the temperature of the cold reservoir. This is now our working equation. All we have to do is we simply need to substitute the temperatures into this equation. However, you have to be careful because this equation will only accept absolute temperatures. If you're given temperatures in degrees Celsius, you have to convert them to Kelvin. Substituting, in the numerator, our TC is 20 degrees Celsius plus 273.15 to make it Kelvin. In the denominator, you don't need to convert them to Kelvin because this is a difference in temperature. So the conversion of plus 273.15 will only cancel in the denominator. So this is 33 minus 20. Our COP is 22.55. This is the maximum possible efficiency for an air conditioning unit that is maintaining 20 degrees Celsius in a cold room against an external temperature of 33 degrees Celsius. That is how we utilize our equations for determining the COP of refrigerators. Let's go back. Let's answer number 2. A Carnot engine receives 250 kilowatts of heat from a reservoir at 525 degrees Celsius and rejects heat to a heat sink at 50 degrees Celsius. What is the rate of heat rejection and how much power was extracted? For this problem, we will now be mixing the terms containing temperatures and the terms containing energy flow. So now we have a Carnot heat engine. If you take a look at the diagram, this is different from our previous example. We are taking energy from the high temperature reservoir and processing it to become work and heat rejection to the cold reservoir. The temperatures of the cold and hot reservoirs are given, as well as the rate of heat absorption from the hot reservoir, that is 250 kilowatts. We are required to solve for the rate of heat rejection, that is QC, and the power generated, that is W. For this, let's first define the efficiency of a heat engine. For a heat engine, what we want is the work generated, and what we paid for is the QH, or the heat absorbed from the hot reservoir. We can rearrange this equation to solve for the work generated. That would be work is equal to efficiency multiplied by the absorbed heat from the hot reservoir. Now for this example, since we are dealing with a Carnot heat engine, this efficiency is the Carnot efficiency. And we can directly solve for the Carnot efficiency just by using the temperatures of the hot and cold reservoirs. To recall, the Carnot efficiency of a heat engine is equal to 1 minus temperature of the cold reservoir over temperature of the hot reservoir. So we simply convert the temperatures in Kelvin and we can substitute them directly into this equation. That will be 1 minus temperature of the cold reservoir, that is 50 plus 273.15 Kelvin, divided by the temperature of the hot reservoir, 525 plus 273.15. The Carnot efficiency is 59.51%, or that is 0.5951. This is the fractional Carnot efficiency. We simply have to substitute this back as the value of the efficiency. We can now determine the amount of work generated. That is Carnot efficiency multiplied by the rate of heat absorption from the hot reservoir. Our work done or generated is equal to 149 kilowatts. Now, to determine how much heat was rejected to the cold reservoir, we simply perform an energy balance. Our energy balance in this case is the amount of heat absorbed from the hot reservoir is equal to the amount of work generated plus the amount of heat rejected into the cold reservoir. Rearranging this becomes QC is equal to QH minus W. Our QH is 250 kilowatts. We simply subtract our answer from the W. The rate of heat rejection, QC, is equal to 101 kilowatts. That is how we use the equations pertaining to heat engines. Okay? Keep in mind that this analysis is only valid if you have a Carnot heat engine. If you only have a heat engine, you cannot equate its efficiency with the Carnot efficiency. Always remember that the Carnot efficiency is the maximum possible efficiency of a heat engine, and that is only possible if you have a Carnot heat engine. Let's go back and have the last problem. A power plant operates with the heat source at 350 degrees Celsius and the heat sink at 30 degrees Celsius. Its thermal efficiency is 55% of the equivalent Carnot engine for the same reservoir temperatures. To what temperature must the heat source be raised to increase the thermal efficiency of the plant to 35%? In this case, we have a heat engine that is not operating at Carnot efficiency. We know that because it was stated that the thermal efficiency of the plant is only 55% of its equivalent Carnot efficiency. Let's try to solve this problem. Here's the given for our problem. Again, we have a power plant which can be modeled as a heat engine operating between reservoir temperatures of 350 degrees Celsius for the hot reservoir and 30 degrees Celsius for the cold reservoir. It was stated in the problem that the efficiency of the power plant is 55% of its Carnot efficiency. We are required to solve for the temperature of the hot reservoir needed in order to have a plant efficiency of 0.35 or 35%. So the logical way to approach this is first solve for the Carnot efficiency, and then for that determine the actual efficiency, and then later determine how can we increase the actual efficiency of the plant. Let's begin with the Carnot efficiency of the plant, that is 1 minus Tc over Th. We can substitute immediately, that is 1 minus the temperature of the cold reservoir is 30 degrees Celsius plus 273.15 divided by the temperature of the hot reservoir, that is 350 degrees Celsius plus 273.15. Our Carnot efficiency for the base case scenario is 0.5135. Now, it was stated that the actual efficiency of the plant is only 55% of this, so we multiply this by 0.55. The actual plant efficiency currently is at 0.2824. Now, we want this to increase to 0.35. For this to happen, we simply need to determine what is the Carnot efficiency at this plant efficiency. So if your plant efficiency is 0.35, what is your Carnot efficiency? We can simply back substitute this to our earlier relationship between the plant efficiency and the Carnot efficiency. Substituting, our Carnot efficiency is simply 0.35 divided by 0.55. For our Carnot efficiency should be 0.6364. For this amount of Carnot efficiency, we then need to determine what is the temperature of the hot reservoir. For that, we have to rearrange our earlier equation for the Carnot efficiency. This will be 1 minus Carnot efficiency is equal to Tc over Th. Rearranging once more, this is Tc over 1 minus Carnot efficiency. This is equal to the temperature of the hot reservoir. Substituting, this is 30 degrees Celsius plus 273.15 to convert it to Kelvin divided by 1 minus our new Carnot efficiency, that is 0.6364. So based from our calculations, the temperature of the hot reservoir should reach 833.7 Kelvin in order for us to have a 35% plant efficiency. Let's convert this to Celsius. This is minus 273.15. Our temperature should be 560.6 degrees Celsius. So this is what we have been talking about earlier. In order for us to increase the plant efficiency, we need to increase the temperature difference between the hot reservoir and the cold reservoir. In the previous case, our delta T is only 350 minus 30 degrees Celsius, that is 320 degrees Celsius. And the corresponding plant efficiency for that is 28.24% only. If we increase the temperature of the hot reservoir to 560 degrees Celsius, that gives us a delta T of 530 degrees Celsius, and the corresponding efficiency of that is 35%. Okay, so that is one way on how we can increase the efficiency of a heat engine. However, the question here is, up to what temperature can we increase the temperature of the hot reservoir in order for us to continuously increase the efficiency of the plant? Now, 560 degrees Celsius is still attainable because this can be the combustion temperature of a certain fuel. However, as you go higher and higher, it becomes more difficult to sustain a higher temperature. So besides from attaining a large thermodynamic efficiency, we still have to consider other factors for this generation of energy. Okay? Always keep that in mind. Let's go back for some key takeaways. Let us end this lesson with a summary of the takeaways. First, the Carnot cycle is a four-step theoretical thermodynamic cycle that generates work from an input of heat with the rejection of waste heat. Next, the reverse Carnot cycle consists of the same four steps but in the opposite direction, which uses an input of work to accomplish a non-spontaneous flow of heat from low to high temperature reservoirs. Next, the Carnot efficiency is the maximum possible efficiency of heat conversion for a specified set of heat sink temperatures. And then the reverse Carnot efficiency is the maximum possible COP for refrigerators and heat pumps. And finally, the efficiency of a real cycle cannot exceed the Carnot efficiency. That will be a violation of the second law of thermodynamics. That's it for this lesson. I hope you have learned something. Thank you for listening, and as always, keep safe.